Good afternoon, everybody, or good morning, as the case may be. I'm giving this talk as part of the Gold series, which Neil Phillips organized, but for various reasons, this got tacked on as a sort of a late edition. And so what I've done here is I've tried to give a conventional view of the understanding of gold and gold distribution in the Witwatersrand, more the traditional view of the kind of Maurice Viljoen view of how things might have played out, rather than the more chemical views that seem to have been posited by many of the speakers in the series. But first of all, let me just say a bit about myself. I'm Terence McCarthy, Spike McCarthy. I was spent my entire academic career at Wits University. I was head of the school for 17 years. I've had wide interests. I've been working in the Wits for a long time. My very first Wits paper was in 1982 on Langemanskop. And my most recent one was published just a few weeks ago with Neil Phillips. So I've been steadily churning away at the Wits Basin, in addition to a lot of other things. And one of my other big research areas has been in the Okavango Delta. But on with the present one. This talk is, as I say, it's more of the classical view as posited by Maurice Viljoen and many other people. It's dedicated to my very best friend, Jochen Schweitzer, who died last month. And he was a great proponent he spent most of his career, in fact, working on the Wits. And he's a great believer in conventional sedimentology as a guide for mineralization and mineral distribution. So the next slide will be, if you could just switch on to the next slide, please. Sorry, you've jumped one. Right. First of all, let's get terms right. This is our conventional idea of the Wits Basin and all its different component parts with the different gold fields, each one separate. And it's got here the production from these various gold fields. Just to give you an idea of the scale, the magnitude of this unbelievable accumulation of gold compared to, say, Kalgoorlie and Homestake mines. They just pale into insignificance compared to most of the individual gold fields, even of the Wits Basin. It's an unbelievable resource, and certainly unique in the world, obviously. And it's of great interest economically and also geologically. Next slide. Okay, so the question is, how extensive is the Wits? How big is the Wits Basin? You know, if we think about Wits Basin sizes, we say, how big is the Transvaal supergroup? And it's massive. Or the Karoo, for example, how extensive is the Dwyker? And we look at the Wits Basin, as we've just seen there, and it looks tiny in comparison. But is that really a reflection of the true size of the Witwatersrand Basin as it was in the past? And colleagues and I have looked into this. Can you look at the next slide? We've come up with this map here, which shows that, in fact, the Wits Basin probably had many, many small parts. It's highly fragmented for tectonic reasons. And we believe that there's still a lot of potential here for the discovery of new Witwatersrand basins. It extends all the way from the far north, the Buffalo Springs area, down through Costa, all the way down to the southern boundary of the Craton, and of course out to the Lebombo Range on the KZN coast. So it was a very, very extensive basin, in fact. And that little piece that we see is just a tiny fragment of what was once the Wits Basin. Next slide. If we look at it in a global sense, if we do the reconstruction of Overberg, this was an idea that was originally proposed by Eric Cheney, and he put the Pilbara Craton just due south of the Bethlehem Basin, sorry, of the Carlsberg Basin. Then the other guys came along, the guys from the UJ came along, and they put the Pilbara way out in the west, and the guys from Curtin University put it way out in the east. But my preferred choice is, as you see it there on the screen, in that embayment in the Carpal Craton. And that fits quite nicely because the greenstone terrain the Pilbara is very, very similar to that of Barberton. And in fact, Eric Lowe, John Lowe has identified spherular layers, 3 spherular layers, which he dated in Barberton, and the same spherular layers with the same ages have been found in the Pilbara. So I think that's probably the fit between the two. And of course, it fits very nicely with the Transvaal and the Ventersdorp fit quite nicely with their counterparts in Australia. And of course, we know that underneath the Transvaal and the Ventersdorp, we've had lots and lots of interesting little additions to the Witwatersrand Basin, and one can only wonder what's sitting there under the Hammersley and the Fortescue in Australia. Because we know we've got the De Grey and the Nullagine, which contain gold-bearing conglomerates, and they would fit, they correlate somewhere with the Wits, but how exactly we're not sure. So there's a fair chance that the Wits Basin, in fact, extends across into what's now Western Australia. Next slide. Okay, the Wits, I'm not going to talk too much about the detailed sedimentology, but the Wits, as you all know, is really divided into 2 parts. There's the lower part, the Witwatersrand group, which formed during a fairly substantial marine transgression across the Craton. And then the Craton began to fragment into a number of subbasins. And in each one of those, a sequence of more proximal sediments formed, and they constitute the central Rand group. So that's shown there in yellow, and the Witwatersrand group in brown. Next slide. Okay, so what I've got to do, I'm going to emphasize the tectonic events, because this talk is about tectonism and its effect on gold mineralization. So I've divided these tectonic events into, I think there are 5 in all that I've identified. And unfortunately, a lot of these hydrothermalists have kind of confused these different events. They don't recognize the time or the significance of the time interval that's expressed here, and also the nature of the events. They say that thrusting was an active pathway for fluid flow, without saying which type of thrusting and what age. We'll see as I go along with the several different ages of thrusting, and each has had a different effect on the basin. Next slide. All right, so the breakup of the fragmentation that initiated the deposition of the central Rand group was characterized by basement uplifts. And here I've shown some of the more important ones. And they're all characterized by the development of these huge monoclinal faults. And they ring the basin, and each one of those monoclinal folds hosts in this interior a smaller sub-basin, and it's in that sub-basin that these various gold fields are developed. The best known of the sub-basins is the border structure, which is the one that flanks the Welkom goldfield in the south. And I'll talk quite a bit about that. But in addition to, it's not just simple thrusting. These things have a strike-slip component, which is shown there with the strain ellipse. The east-west ones are left lateral, and the north-south ones are right lateral, producing a shear couple. And this has also had a profound effect on the distribution of gold down at the stope level. So we can see in the Witwatersrand the effects of tectonism on a scale of entire gold fields, and we can also see it down to the scale of individual stopes. Next slide. All right, so the border structure, as I mentioned, is the best documented because it's been drilled off, and it's about 4 kilometers tall. This is a massive structure, and developed mainly during Central Rand Group times. And the one thing that people neglect is that the thing is very eroded. And in its day, when it was still growing and active, it would have formed quite an impressive mountain range, possibly several thousand meters tall. Now, you must remember that the Earth was much cooler then. You know, there's this notion that the sun was much less luminous, by about 30%. It's called the faint young sun hypothesis. So the border structure would have, in fact, been a ridge, a mountain range, actually, snow-capped, with glaciers. So the idea of, quite an old idea of that glaciation has played a significant part in the sedimentation of the Witwatersrand Basin aligns with this notion of what these monoclinal folds would have looked like at the time of deposition of the central rand group. Next slide. Okay, there's an example, a modern day example of this in New Zealand. There's a massive structural fault that runs down the length of South Island, New Zealand. And so that one happens to be a transform fault. And it forms this massive mountain range called the Alpine Range. And there you can see a photo of it from an aircraft. And so it's snow-capped and coming off obviously a lot of sediment. And that sediment forms these massive alluvial plains on both the eastern and the western sides of New Zealand. So that would be a kind of a view of what the Witwatersrand Basin or the Velkom Basin basin margin, the border structure may have looked like during central rand group times, with a big alluvial plain in front of it on which the gold deposits were being laid down. Next slide. So looking at it in plan view and looking at the monoclinal folds that we know of, this is the distribution. So these green patches would have been mountain ranges, all snow-capped probably. So there would have been quite a scenic place, the area in which the Wits Basin was forming. And with snow-capped and these huge alluvial plains all around, separating these snowy mountain ranges. Next slide. Okay, so the gold was probably laid down primarily during central rand group times. And the gold, of course, is characterized by the presence of quartz, vein quartz, and gold conglomerates. And, you know, people have always wondered what is the source of this gold? What's the source of the quartz veins? And the only conceivable place where they could have come from is from the small masses of veins that occur in the lower Wits, of the kind that Fred Struben mined at his mine near Vredefort there. And they have been eroded out of lower Wits and critical other lower formations of the Wits, and have deposited as conglomerates in the central rand group. So the whole thing is internal. The gold and everything else is internally derived. Next slide. Okay, one of the important things about the Wits is this tectonism that was taking place resulted in a lot of transgressions and regressions and reworking and so on. So we get these fan conglomerates that represent multiple episodes of reworking. And the time is another very important factor in the Witwatersrand story, because we know that it must have lasted, the deposition of the central rand group must have lasted for a considerable period of time, and much longer than the thicker West Rand group. And we can see that, for example, in the absence of feldspar in the upper Wits. People say it's hydrothermally altered. I say it's altered by climate, but exposure, time exposure. So there's been less of it there, and it's simply just decomposed because it took so long to deposit. Anyway, so we have these fanned unconformities. Those are characteristic of all the gold fields. Next slide. And here's a nice example. This is from the Velkom goldfield, where we have in red is the mined out area of the basal reef, which is the main gold bearing horizon there. And that's cut off by the leader reef. The leader reef contains no gold up dip of the unconformity where the two come together, but down dip, the gold that was in the basal reef has been reprocessed and is now present in the leader reef. So the leader reef is mineralized beyond the subcrop, but not upstream of the subcrop. So this is an example of the recycling of gold. It's just stayed in the system while the rocks below have been eroded away. It's survived in the system presumably because of its density. Next slide. We also have these big alluvial plains, which is what the basal reef and many of the others would have looked like. The very extensive alluvial fan type deposits, and they contain ribs of gold enriched and gold depleted zones. And they gradually get more and more less pronounced as you go towards the more distal parts, and eventually they fan out and possibly culminate in a kind of a shoreline type deposit, which doesn't contain economic mineralized gold. That's the East-Rand Basin. Next slide. The Kimberleys, that was the Nigel Reef, or the main reef, as some people call it. Then we've got the Kimberley Reef overlying that, and that's more channelized in the East Rand. As you can see here, this is the dark areas are the mined out sections of the Kimberley. Either it's very, very thinly developed or not mineralized at all, or not developed at all, actually, outside of the mined out area. Next slide. It's channelized, as you can see. This is the reef thickness on the left, and it's thickest in the proximal areas, and then develops, it becomes thinner, and it's channelized into thick and thin zones. And you can see the gold tends to follow the thinner reef. The thinner the reef, the higher the gold content you can see on the right-hand side. Next slide. If you look at this channel width is reef thickness versus grade on a basin-wide scale. This is for the entire Evander Basin. You can see this kind of relationship where thin reef is generally high in grade. Not always, obviously, you can get thin reef and no gold at all. And thick reef is generally of lower grade. It's kind of a relationship, but there's no mathematical significance really, because remember, it's filled, all that space below that curve is actually filled with dots. Next slide. Okay, so how did this develop? What is the sort of controlling factor on this this thick-thin relationship? And colleague of mine, Paula Ogilvie, came to the idea that if you have a flat sheet, like if you put a towel, say, on a flat table, and you give it a bit of a sort of like a strike slip type shear couple, then it folds itself into a series of ridges and depressions. And the active sedimentary surface would have presumably done the same thing during sedimentation because of the right and left lateral nature of the movement. So you get some parts that are being pushed up, other parts that are sinking, and that causes differential erosion. So you get the thinner parts, which are the crests, getting more erosion and therefore have higher grade. So that was a cartoon of how it probably worked in settings like this. But these are now, we're looking at small scale things here, stope scale, and even with sub-stope scale type things. Next slide. You can see that on the basis on gold fields as well. This is now the whole of the Central Rand. This is the main reef all the way across the Central Rand from DRD right the way through to the border of EM on the right-hand side. And again, you can see there's an orientation, a preferred orientation toward northwest, southeast, both in the grade and in the reef thickness. Next slide. This has been measured up. Richard Stewart did all this work for his PhD, and he measured up all the orientations, and you can see the parallelism of the channels and the gold pay zones line up all in that northwest southeast direction, which is the line set by the shear couple that operated across the Central Rand and the whole of the Wits Basin, actually, during deposition. Next slide. This is the main reef, the main reef leader, rather. The previous slide is the main reef, which sits underneath this. And this is, again, the same sort of picture for the main reef. You can see the channelization with well-developed channels separated by poorly developed reef zones in exactly the same orientation as we saw in the previous slide. Next slide. This is a different reef. This is the Cook section, which is part of part of the the West Rand system. You can see there the monocline with the pinching out or the thinning out of the reefs onto the monoclinal structure. Paleocurrents are from left to right. Well, yeah, left to right. And you can see the pay shoots correspond to that, very nicely defined and in aligning up with the sedimentary depositional conditions. Next slide. Okay, now we've got all these separate basins, and as I mentioned, they are separate basins, but some of them are completely separate. Like, for example, Evander is completely detached from the others, whereas Eastrand Basin is, or Southrand Basin is also completely detached. Eastrand Basin is partly detached, and then you get other basins, like, for example, the Welkom, the Free State Basin. The Welkom Basin is completely detached from the others, but stratigraphically they have a kind of a uniformity that extends across the entire basin. And this is a compilation of a stratigraphic correlation, which was done by Jan Nelson and Nick Bjerkes some years ago. And it shows the relationships across the entire known Witwatersrand at that time, all the way from the Free State right through to Eswatini, Swaziland. So they correlate, but the units appear and disappear, and the thickness changes and so on. But you can still identify the stratigraphic units right across the entire area. Next slide. And there it's what is that? This is how Sachs correlated the reefs all the way around that ring. And there is a pretty good agreement as to the correlation of individual units, although the thicknesses do vary quite a bit, and some of the units appear unique to particular stratigraphic sections, others are absent. Next slide. Okay, the other one, the carbon enigmas, people spoke about this in various talks. You know, carbon is obviously associated with the gold, everybody knows that. And people argue a lot about it and where it came from and so on. But to my mind, the thing that really will play a heavy role in trying to understand carbon is the field relationships, the actual interrelationships of carbon with gold. Now, the problem with carbon is it's quite mobile. And a lot of the structures we see in carbon, like, for example, this the columnar carbon, you know, which Holbauer thought was the algal structures, in fact, may simply reflect a tectonic phenomenon, because always perpendicular to some fracture plane or bedding plane. And it may be, and maybe they're behaving like asbestos. You know, asbestos forms fibers, or it can form, if you take something like chrysotile asbestos, it can be in a smooth form, or it can be in a fibrous form. And that depends entirely on the structure. So the fibrous carbon may actually simply be an expression of tectonic effects. And that may explain why we get it. And then the gold, the association with gold is the other important issue. Next slide. And this is a very nice sample that Bruce Cairncross showed me. The top figure on the right, there's a slice through a conglomerate reef with a carbon seam in it along the bottom. You can see it quite clearly. And the carbon seam has got a thin ribbon of gold at its base and a thicker cap of gold. And that cap runs all the way across. There's a lot of pebbles that break it up. But the carbon itself is actually fully impregnated with gold. If you look at the bottom picture where it's looking reflected light, you can see that that carbon is in fact also mainly gold. But there's enough carbon there to see the black color. So what is that? Now, there are different ways people have looked at this. And the popular belief now is that the carbon comes from oil, infiltration of oil during basin maturation. You have expulsion of oil. And then this is followed by either separately in one model by separate solutions, one containing uranium, the other one containing gold, and they precipitate along with the carbon. The other one is that the uranium is detrital. It causes the radioactive decay. It causes polymerization of the organic molecules in the oil and causes clumping. And then later on, a gold-bearing fluid comes through and deposits as gold gets precipitated by the organic, as in carbon in pulp. The other possibility, and which some people still subscribe to, is that the gold was formed in a single process. single-stage process by a metal hyperaccumulating bacterial mat. That was the Laurie Minter's view, and others as well, Monson and so on, have postulated that as an alternative. Now, if we look at the scale, you say we've got carbon, you have extensive areas, like, for example, the carbon leader in the Welkom goldfield, in the Blocksdorp goldfield. Let's have a look at a modern day example of what this might have, what this could represent. If we look at the next slide, this is a place in Iceland. Iceland is obviously there's no trees or anything grow there. The only thing that grows there is moss and lichen. And this is it's a place called the Skydra Sanda, and it's an alluvial plain. It's about 1,000 square kilometers in area. And the only thing on its surface is channels, as you can see there, all these channel systems. But the rest of the surface is dusted with lichen and moss. Now, in the Archean, there wouldn't have been lichen and moss. They would more primitive life forms, and that would have been bacteria. So the equivalent of this formation, this unit in the Archean, would have been an alluvial plain covered with bacteria. And if that bacteria was a metal accumulator, as many bacterial species are, then you've got the ideal site for the formation of carbon and carbon metal associations. So if you look at this picture, you can see the green sort of haze just showing through in various places on the fan surface. It's not a proximal distal thing. The alluvial, the fan, those plants grow everywhere over the whole fan surface. Now, if that were covered by, let's say there was a marine transgression and sudden rise or not sudden, a slow rise in sea level, then it would bury that carbon layer with all its entrained metal, and it would make a carbon seam. So it doesn't require much imagination to see what potentially a carbon leader might form from in an environment like this. And remember, with the evidence that I've spoken about earlier, suggests that we were in a terrain which was pretty cold and mountainous. Next slide. All right, so that basically concludes the Witwatersrand itself. Next event in the story is the erosion, planation of all those earlier structures, and eventually the eruption of the Klippruff-Vuursberg lavas. So the Klippruff-Vuursberg starts with a period of erosion, and this has been well studied by Mike McWar and his various colleagues down at in the Carltonville area, in the Carltonville goldfield. Next slide. And Mike has been able to actually winkle out the topography, the paleotopography of the channel systems on which the VCR formed. And you've got these modern analogs would be terrace gravels with slopes and so on. And they use this, in fact, now for Fassie's definition. There's a very, very strong correspondence between the paleotopography at meter scale and the gold concentration. So that was clearly an erosion surface and strongly influenced by normal fluvial processes. Next slide. Okay, that was followed, the erosion was interrupted by the eruption of the Klippruff-Vuursberg lavas. And then a period of extension, regional crustal extension appeared on the scene, much like the Basin and Range province of Colorado, and formed a number of these grabens. Some of the earlier thrust faults, like, for example, the Blockberg thrust, were reactivated as normal faults. The one that runs through Joburg, we've got one of these big thrust faults coming through Joburg, the Rietfontein fault system, that also became a big graben structure. And then you had others of these big detachment surfaces. Martin de Wit has written about these using the seismic data. And you can see this, the breakup of the whole craton into a series of horsts and grabens. Okay, so these reactivate the older thrusts as normal faults and create a whole lot of new normal faults as well. So the debris flow fans then fill up all the basins, but there's no gold mineralization associated with this. The only gold associated with Ventersdorp is related to the erosion surface, which preceded the eruption of the basal lavas. So it's all derived from the Wits. Next slide. So if you look at the cross-section through the Free State goldfields, you can see here, this is compiled by Laurie Minter and augmented by myself. On the left-hand side, you can see the effects of the border structure, the big fold, the monoclinal fold. And then we have these masses of normal faults. And going across to the right-hand side into a dome, which marks the opposite edge of that particular depression, which gave rise to the Free State goldfield. Now here we had the fortunate situation where the breakup of Horst and grabens, the formation of Horst and grabens during middle Ventersdorp times was very beneficial because it meant that the strata, the gold-bearing strata, would continually being brought back to surface by these normal faults. Unfortunately, this never occurred in the Carltonville or the the Central Rand goldfield. So there the ore zones get very deep, and they're going to eventually run out of will no longer be economic, which is a pity. At Evander, they also had this Horst and graben faulting, which kept the reef at relatively shallow depth. Next slide. Okay, the next event is another major erosional event, which is the onset of the Tunis-Poort group, the deposition of the Dolomites. And again, that begins with a period of erosion, and the debris eroded from the footwall, which included in some places Witwatersrand strata, accumulated gold, and that gave us the Black Reef. So the Black Reef is patchily mineralized, often channelized, or locally in form of extensive sheet deposit. But again, the gold is coming out of the Wits. Next slide. You can see that quite nicely, the channelized effect. Here's a nice diagram from Papenfuss, 1964, which shows the channels out in the West Rand, channels in the Black Reef, which coincide more or less with the subcrops of the Witwatersrand, gold-bearing Witwatersrand strata beneath the Black Reef formation. Next slide. Okay, so by this stage, all the gold had been deposited. Most of it, or virtually most, or probably all of it, was deposited during Central Rand Group times. And but there were a lot of tectonic upheavals. We've seen several periods of thrusting and normal faulting of various ages, and a lot of tectonic upheavals. But there was just one more to come, and let's have a look at that one. Next slide. It was the Vredefort event, which was impact probably of a maybe an asteroid hit South Africa and made a huge hole, which is called the transient crater. And that, of course, caused a lot of pushing of material away from the hole and created thrust faulting on a massive scale. And then, of course, we have the rebound, the central uplift. You can see it there, illustrated quite nicely by a drop of water. And that would have brought everything back. It would, all those early thrusts may have been reactivated as normal faults. And then we have finally the collapse of the crater itself and the formation of ring faulting. So that would have been the sequence of events that surrounded Vredefort. Next slide. If we peel off all the cover, that's what it looks like. Vredefort, you can see the central uplift there, and it's surrounded by a series of anticlines and synclines of increasing amplitude as you move away from the core. And it's also that's asymmetric. See, it's developed more on the northwest side, and the reason for that is that the whole basin has been tilted by about 3 degrees and eroded off so that the other part of it, the other half has been eroded away and is gone. So we only see the one half of the structure preserved. Now, the effects of Vredefort are quite far-ranging. And next slide. They extend. We can see them extend to varying intensities at quite far away. If we look, for example, at the East-Rand Basin, East-Rand Basin is a highly folded zone, and it's got thrust faults, lots of thrust faults which verge towards the northeast. So associated with the formation of these folds are thrust faults, basal thrust faults, and they give us an indication of the quite distal effects. But the kind of effects that formed depend to a large degree on the lithologies involved. So here the dolomites were quite amenable to deformation. If we go around the basin, we look there, for example, at the Carltonville Goldfield. There we have quite dramatic effects because the main plane of movement was in fact on the contact between the Witwatersrand and the Ventersdorp. Because the Ventersdorp there, the basal Ventersdorp there consists of very mafic lavas, serpentinites actually. So we have a lot of thrust movement on that basal unconformity. So there's the VCO in particular is quite heavily faulted. And then coming around to the Klerksdorp Goldfield, there the faulting is, the stratigraphy is more or less resistant to the thrusting, so that we just have far less deformation than we find, for example, at Carltonville. Free State has very little effect because it's so far away. It's very little effect of Vredefort down there. Next slide. Okay, you can see the varying amplitude of the folds in this map here. And the top on the right-hand side, you've got the fairly heavily folded East-Rand Basin. And then we get this, there's another broad sub-basin, which appears to be more open type folding. And then we go around, as you go around toward the northern edge of the basin, we swing around in the direction of folding changes. We get that big Soweto syncline and the Doornkop thrust fault and so on, which are directly connected to the Vredefort core, which is in the bottom left corner. So yeah, so that's the distribution of the effects of Vredefort. Next slide. All right, so what do we conclude from all of this? We can see that the deposition of the Wits began with a major marine transgression. This gave rise to then it began to fragment into a number of sub-basins. These very tall monoclinal folds associated with these basins probably developed ice caps. So we have a sort of a glacial environment which is consistent with the glacial theory of Witwatersrand deposition proposed in 1955 by Wiebels. And it's probably correct, and that's the source of the cold weather and the glaciers. The abundant quartz veins in the lower Wits were obviously eroded from the upfolded areas of those monoclines, and that provided the raw materials for the quartz pebble conglomerates, which we see in the upper Wits. Now, there's a lot of gold there, and there must have been some processes operating that accumulated gold more than just normal detrital gold. So it looks possibly as if there was some unusual condition in the atmosphere or in the water. At the time, there may have been cyanide present in the atmosphere and in the water, which promoted solubility of gold. So that gold, during normal weathering of rocks, gold would be rendered into solution. But then these hyperaccumulating bacteria would take it out of solution and form it into lumps, which could then be worked detritally. So something like that probably has contributed to the significant quantity of gold that accumulated at that time. Okay, so the most of the gold, virtually all the gold, was accumulated during that basin, those sub-basin forming events. and they are well, so they've connected tectonically. They've got a similar stratigraphy, so they must have been all responding to the same kind of crustal forces operating at the time. There's several major geological episodes that occurred after the deposition of the Central Rand Group, which are associated with gold, but the gold itself is derived from that initial phase of sedimentation. But the long sequence of events involving two large igneous provinces, marine transgressions, a carbonate platform, and a major meteorite impact expanding over something like 1,000 million years, almost. And, various people have proposed that different fault systems were fluid pathways for various events, but I think not enough recognition is given to the timing. And so we can see, if we look at the events in detail, there's a very close correspondence between the tectonism, the sedimentation, and the golden currents at all scales, right from stope scale up to regional basin-wide scale. So there's a very strong dominance of sedimentary processes in shaping the distribution of gold in the Witwatersrand. Thank you. My talk. Okay.
Thank you very, very much, Professor. I found that slide of yours introducing the Vredefort quite fascinating, a beautiful slide to do that with. I have one final question for you before we end off. You intimated earlier on that, and thank you very much for helping us redo this recording, that you said there will be some differences from what you said earlier to this one. Yeah. Do you care to just wrap up by pointing out the differences that you brought in today?
Yeah, look, the primary differences were related to the erosion of those monoclines and the fact that they had a severe, significant topographic expression. And there was always this, the idea of glaciers having been involved in the formation of these alluvial plains, which Wiebels proposed in 1955. Where would the mountains have been? What could have made those mountains? And now we can see what made those mountains and why they are where they are. So that's I think a significant contribution, a significant new way of looking at the Wits, of seeing it in a glacial kind of context. And the same goes for the carbon. If we look at Iceland, we're going to learn a lot of things that we see in for example, the carbon leader. We can see the potential by studying those barren plains, or not barren plains, they're not barren at all, but in those big Icelandic glacial outwash plains. And the other place where we can learn a lot, I think, is from New Zealand, from the Alpine range in New Zealand, because I think there's quite a good idea of the kind of environments which may have existed during the Witwatersrand times. Yeah, so those new ways of looking at the Wits, which sort of fit in, I think, nicely with some of the really old stuff, old traditional views.
Thank you very, very much once again for taking out the time to help us, and you've left us with lots of thought and fertile ground for discussion. Thank you once again.
Thanks for making this possible. Thank you.